that's looking at this duality in linear programming. So as I said, in the literature, min-max theorem was studied first from Newman. At that time, these linear programming hadn't been sort of invented yet. So therefore, the duality hasn't been sort of introduced just yet. But later on, they sort of discovered that, in fact, they are same thing. So min-max theorem is sort of same as the dualities, happening in the linear programming, precisely because of duality in the linear programming and cause this sort of min-max theorem. So the duality is one of these most important discovery, in the development LP, and basically said that for each linear programming problem, it will be associated with another linear programming program is a dual, right? And they are primary to each other. In other words, that this original linear programming problem we called primary problem, and the dual we call it dual, and the dual's dual is actually primary as well. So you can actually they can call each other dual, primary. So this is just example. Let's say you got this primary problem, and this dual problem is really just reshuffle these sort of their parameters. Like for example, the C here, right? You got this in part of the maximization, but here is is part of this equality, part of constraint. So this B was originally in the constraint, and now sort of the dual problem is basically in this objective. And then you have this X and Y sort of different parameters to optimize. So this is sort of you can write a different form, right? You can write it in the matrix form. You can write it in this other form like a matrix and so on. But the relationship is really illustrated here. So you basically got a matrix here, right? And you got the X, which is the primary problem you want to get. The dimension is basically this matrix, the different sort of columns, like number of columns. A number of rows is basically dimension of Y's, which is sort of a dual problem. And then you got this equality constraints. Because this constraint is basically the B and the sort of a variable B and variable C's. So let's also have some more definition. So feasible solution for a dual problem, and those are the ones that satisfy the condition of the optimality for the primary problem. So the feasible solution dual are those that satisfies condition of this optimal optimality of the primary problem. So in other words, that's the optimal ones are the feasible solution for dual problem. So the maximum value of that in the primary problem equals the minimum value of the W in the dual problem. So if you think about this, right, if you write this as a form of max and min kind of problem, and then the maximum value of that you obtained, okay, in your objective would be equal to the mean of the value that you obtain in the dual problem. So that is the strong duality that's specified in the LP. So try to sort of illustrate these two sort of duality is that, so from the primal, right, because of this AX always smaller than B, and you can have this condition codes, and you can also have this condition codes. And by have these two together, you basically say, okay, I have this matrix A and have this Y and X multiplied, and I would be sort of in the space. The range of that would be sort of bounded by the CX and YB, right? The upper bounded by YB and lower bounded by CX. And so this is for any, sort of a solutions, XY feasible solutions right? But for optimal ones, then that equality would hold. For the optimal one, that equality would hold. So with this sort of in mind, then actually we can looking at go back to our original problem. We can sort of understand the reason behind it. So this duality, you can actually write it down in the formula of equation 5 and 6. Is that one, if your xj is larger than 0, and you would make sure that this equation holds. To make sure that this would be the condition that would be fulfilled. This is coming from the dual theorem, and so as I said, the dual. Any pair of the prime or dual problem can be converted to each other. The dual of dual problem is always a prime problem. That's what I just said. So now, with that kind of in mind, this sort of theory in mind, let's go back to the two-player zero-sum game. Okay, so recall we got two players there, two-player game, zero-sum, and there's a matrix. And if the matrix basically say your payoff minus my payoff is always 0, and we can then write it down this role players solution by using LP, right? And if these forced to announce the strategy once, so we can actually write down this. So maximum that is, as I sort of illustrate, maximum of that is actually same as sort of say, I want to find a solution X, and that's my, here I want a solution X that is basically is to maximize a lower bound of these role player gonna come out with, because this role player is going to minimize that reward, whereas the column player try to maximize it. But if you're just looking at this LP, though, is that you don't really sort of say this implicitly that you really rely on this role player to really maximize it, but rather say I can set up a lower bound, right? Therefore, I want to maximize that lower bound. So that's the LP1 from this. That's the IP1 from role player. Then we can actually write it down his dual, right? This dual is basically this. Is that I want to minimize Z prime, and this is sort of follow exactly as this LP that LP this prime or dual kind of relationship. I can do that, and we can do a bit of sort of a transformation, because this is not necessarily exactly what we want, but we just want to sort of looking at it from our gaming perspective, is that we introduce this Z that's double prime here, is that and then we also basically say introduce this C matrix, which is say this zero-sum game, right? We need to introduce this payoff for second player, which is defined as negative of R. And so basically we change this LP to LP3, right? LP3, which is the same as the LP problem we formulate from role player, from the role player perspective, right? From the role player perspective, is that they want to maximize this Z, double prime, let's say. They want to, from their perspective, they want to maximize this. They also do this max min kind of strategy, but you can actually change it to min max if you from this column pair, role player perspective. So really depend on how you're looking at it. If they all from their own perspective always maximize, but if you from the opponent perspective, you are actually minimize that. So the LP3 is nothing but LP that the column player would solve if they were forced to announce the strategy in advance, right? As I said, is is really exactly the same as we just said. There's LP problem for role player and there's LP problem for column pair. So since LP2 is a dual of LP1, LP strong duality theorem basically imply that the solution, okay, you got, okay, the solution you got, this Z is equal to Z prime. Z equal to Z prime. And on the other hand, give our construction of this LP3, it follows that, and if this Y Z prime is optimal for LP2, then Y minus this Z is optimal for LP3 and vice versa, because this LP2 and LP3 they are the same. So then, if LZ is XZ, sorry, if XZ is optimal for LP, Y Z prime prime is optimal for LP3, and they are sort of equal. The value of that is equal. Basically, they are solving this, the same problem. So then it's the theorem, the min-max theorem, basically say solving this min-max is equivalent to solving max-min, and the solution is a Nash equilibrium. So the solution is a Nash equilibrium, and the same case for the other round, right? When you have a Nash equilibrium, that actually it is the solution for min-max or max-min kind of formulation you got. So I think how much time we got? Given the limit time, I written this sort of a sketch of the proof, so you can actually go through it to see that whether you are able to sort of come in with sort of a proof for that sort of theorem. And so you look at that from the one perspective, that's if it's a min-max, then it's a Nash, right? If it's Nash, then whether it's a min-max solution would give you. So yeah, you can have a look on that. So just see if there any question. Okay. So the now the next step is really to try to make sense of it, right? So when you have this LP for this zero-sum game, and what this look like, how to actually solve it. So you can write it down. This, if you have this matrix, then you don't really need to write down the reward for second player, because they just opposite to it. And then you can, based on this R1, right, you can write it down, this primal sort of solution, and then you can actually have the dual as well. Then LP typically solved by simplex solution. So here's a simple example. And let's say you've got this sort of payoff function. If you have that, and let's say you can write it down this as a LP solution, and you can find that actually the optimum solution is this. So which give the value V1 is 0. And this and min-max, in fact, the optimal ones is at the settle point, right? And you can see that at any deviation of the settle point, then the agent would lower his sort of utility, and therefore increase the utility of others. So you can actually think about this from one agent perspective. You can actually try to draw this, because it's 2 to 3D kind of plot, but you can actually map to this one dimension. You can see that. So it's always like kind of these things, that this is the optimal point, that point. If you any deviation from it, that wouldn't give you optimal. And so, yeah, this is sort of in the scalar form, rather than writing in the function, you can actually write it in this for each of these probability value for each of the action, right? You can actually write it down that as S, 1J. So adding them together across all the action, the J is basically for each of the action, then you equal to 1. So then this review are very interesting things happening in your solution. So all of these utility terms U1 are constant in the linear program, right? This is basically specified by the reward function, right? And why this mixed strategy are the variables that you will try to get, right? So what you want to get is this mixed strategy terms, like for each of the dimension, what's the value of it, indicate the probability you're going to choosing that action. And also this U is the one you try to minimize, is basically the value of the value of the game, right? So from this player pool perspective, you want to minimize that is this dual, right? Then try to sort of find the upper bound. You want to minimize that upper bound. So the first constraint states that for every pure strategy J, for like player one, his expected utility, let's see this one, for playing any action J, this is basically say, for play any action J, a given player two's mixed strategy S2, given this players two's mixed strategy, so basically this is the mixed strategy 2, is at most U1. Okay, it's at most U1. So it's basically say I'm going to enumerate all possible pure action that I got. Sorry, I'm going to emulate all possible pure action that I got. And basically to look at that expected value, if the opponent play, this S2K, the strategy, and I will make sure that would be always smaller than, than U1 start. So those pure strategy, because think about this, each of the enumerated this given order J is basically the pure strategy. So this pure strategy of the expected utility is exactly Q1, and will be play one's best response set. So in other words, if you equal to them, would be the one that you would play in the end, right? Because that is a probability you specify there, and the equal to U1 is the one that probability going to reach to that minimum value you will get. So then it's the best response set. So this pure strategy, so here is going to be your, while those pure strategy leading to low expected utility will not. So anything that's smaller than that, right? And then you wouldn't reach to that, then it's not support of that. Therefore, you don't have any probability at all on those pure strategies, and because they can reach that sort of the minimum value that you want to get. So this is sort of a concept of the support and best response set, which will be useful in some analysis about the min-max solution. And so the third thing that I would like to sort of discuss is that the LP will choosing player two's mixed strategy, so which is here, enumerate all possible actions. So this is a mixed strategy. And I'm gonna choosing this mixed strategy, sorry, in order to minimize U1, in order to minimize, because you want to minimize U1, subject to the constraint. Therefore, the minimization and the first constraint state that player 2 plays a mixed strategy that minimize the utility player 1 can obtain by play his best response, right? As I said, this is best response. But this guy are gonna choose in such a way, gonna make sure this upper bound, right? It would be a bit minimized. So in other words, min-max is you want to obtain player's optimal strategy, right? So that's what this underlying algorithm is doing. So this LP gonna do the same thing, right, as before, but just reverse the role of player 1, player 2, and really to try to find out this solution. So to really try to maximize, by maximize this lower bound. You can actually introduce slack variables. So instead of using the equality, you can use the equation and then really see whether there's a support of that or not. For example, here, if there's sort of support of that, in other words, that you calculate this Pew strategy, this Pew strategy would give you, the optimal solution. And then this slack variable, this R1J, would be 0, right? Because that make sure that you reach to this lower bound for that Pew strategy. So this is sort of an exercise that want to make sure that you understand that you can using this to really say, can I come in with an LP solution and so on and so forth.